Using the moment distribution method, analyze the frame shown in figure below and plot the bending moment diagram indicating the critical values. EI is constant. So we are going to look at the steps involved in solving this question. So I will take you step by step. So the first step is calculation of fixed moments. The next step, step number 2, is calculation of distribution factors. Then step number 3 is to carry out moment distribution. Step number 4, calculation of sagging moments. And step number 5, our final step, will be sketching the bending moment diagrams. Now let's look at first step, that is calculation of fixed end moments. So the sign convention I've adopted for my fixed end moments is clockwise moments are positive and anti-clockwise moments are negative. For span AB, I've assumed that AB is anti-clockwise, therefore negative, and BA is clockwise, therefore positive, and for all the other spans in that order. So let me start with span AB. Span AB has 2-point load, W1 and W2. W1 is 15 kilonewton and W2 is also 15 kilonewton. W1 is 2 meters from support A and W2 is 2 meters from support B. So basically the two loads are equidistant from each other. So the formula, I've indicated the formula in the table there, whereby our A1 is 2 meters. Our A1 is 2 meters. Our B1 is 4 meters. That is when you are considering the first point load. Then when you are considering the second point load, our A2 will be now 4 meters and our B2 now again will be 2 meters. So if you substitute the values, our W1 is 15, our A1 is 2, and our B2 is 4 divided by L squared, which is 6. For the first part, if you consider the first point load, you get 13.33. Then the second point load, that is negative 15 times our A2 is 2 times our B2 is 4 squared divided by 2, you get negative 6.67. So negative 13.33 plus negative 6.67, you get negative 20. So now for BA, it will be now the other way around. The formula is WA squared B divided by L squared. Our W is 15. Our A1 is 2 meters, so it's 15 times 2 meters divided by times 4 divided by 6 squared, so you get 6.67. Then for the second part will be 15 times our A2 is 4, 15 times 4 squared times 2 divided by 6 squared, and you get 13.33, and if you add the 2 you get positive 20. Now for BC, there's only one loading, a UDL of 80 kilonewton. So the formula is straightforward, is WL squared divided by 12. So you get negative 8 times 4 squared divided by 12 and you get negative 10.67. So for CB, it will be now the positive 10.67. For CD, there is no loading there. So basically everything there becomes 0. So those are the fixing moments. Now let's go now to the next step, that is calculation of distribution factors. So the distribution factor is calculated as shown in the table. So if the far end is fixed, the K is 4EI over L. So if you are at joint B, BA, the far end is fixed, so therefore the formula is 4EI over L. The same case with BD. But for BC, since the far end is pinned, we are going to have 3EI over L. So if you substitute the value, you'll get, for BA it's 4 over 6, for BC is 3 over 4, for BD is 4 over 6. And if you do the summation for all the K's, you get 2.083. And now the distribution factors For BA, it would be 4 over 6 divided by 2.083, and you get 0.32. You get 0.36 for BC, and for BD, again, is the same as for BA. It's 4 over 6 divided by 2.083, and you get 0.32. Now the next step is to carry out the distribution factors. So you usually prepare a table as shown. You have the joint, you have the member, you have the distribution factor, and you have the fixed end moment. So for our joint A, so we are going to populate the table. For AB, we have a fixed end moment of negative 20. For BA, it's positive 20. For BC, it's negative 10.667. For BD is 0 because there is no loading. DB is also again 0. And for CB is 10.67. So the distribution factors, the ones we have just calculated from the table, for BA is 0.32, BC 0.36, for BD is 0.32, and yes, and we end there. So before we start distributing, and C is pinned, so we need to release it so that we can start carrying out the distribution. So how do we release it? Is by applying an equal and opposite moment. So that's what I've done for and C. So 10.67, you add negative 10.67 and you get 0, and half of that is carried to BC. So half of that is carried to BC as indicated in the green horizontal arrow. So half of that goes there and you get negative 5.33. So now we compute the new moments. So for AB, it remains the same, negative 20. For BA, you get 20. For BC, now you add 10.67 plus negative 5.33 and you get negative 16. The rest of the values now remain 0, and of course for CB now becomes 0. Now let's now start balancing the moments. So we'll start by calculating the unbalanced moment at joint B, and the unbalanced moment is 20 plus negative 16 plus 0, which is basically 4, positive 4. So the balancing moment, therefore, will be opposite in sign. If the out of balance moment is positive 4, the balancing moment will be negative 4. So you're going to distribute this moment according to the distribution factors. Therefore, for BA will be 0.32 multiplied by negative 4, 0.32 multiplied by negative 4, and you get negative 1.28. Similarly, for BC, it would be 0.36 multiplied by negative 4, and you get negative 1.44. For BD, again, you get 0.32 multiplied by negative 4, and you get negative 1.28. So the values I've indicated in the table. So the next thing you do is to do the carryover. So we are going to carry over for AB and BD alone. CB, we have already released it, and it is all therefore 0. So half of negative 1.28 for BA goes to AB as negative 0.64, and also half of BD, the balancing moment there, negative 1.28, goes to DB as negative 0.64. So there is nothing else to distribute. There is no out of balance moment. So whatever now is remaining is to compute the final moments. So the final moments for AB will be negative 20 plus negative 6.4, and you get negative 20.64. For BA, it will be negative 20, no, it will be positive 20, sorry, plus negative 1.28, and you get 18.72. For BC, we have negative 16 plus negative 1.44, and you get negative 17.44. For BD, we have 0 plus negative 1.28, and you get negative 1.28. For DB, you have 0 plus negative 0.64, and you get negative 0.64. For CB, we had already released it, therefore it remains 0. So now we go to the next step, that is calculation of sagging moment. Calculation of sagging moments. For AB, span AB, we have 2-point loads. So the formula, when you have 2-point loads that are equidistant, you multiply one of the point load times the distance A. Our A is from A is 2 meters, where the first point load is from the support. Therefore, if you work out that, it will be 15 times 2. You get 30 kilonewton meter. For BC, we have a UDL of 8 kilonewton meter. The formula for the sagging moment, it's WL squared divided by 8. WL squared divided by 8. Therefore, it will be 8 times 4 squared divided by 8. If you work out that, you get 16. So now we proceed to our final step. Which is sketching of the bending moment diagram. So I've taken an extract of the final moments, the final hogging moments below, in the table below. You can check the table below. So for AB, we had calculated it as negative 20.64. So I've indicated the values for the hogging moments in red, and for the sagging moment in blue. So all the values that are in red are hogging, and all the values that are in blue are sagging. So hogging red, sagging blue. So for AB, we had calculated it as negative 20.64, and I've indicated there 20.64. Then for BA is 18.72, I've indicated there. So for the sagging moment between AB, we have already calculated that as 30. So the sagging moment will look something like a trapezium, as shown in the diagram. For BC, it will be 17.44. For BD is negative 1.28, and DB is 0.64. The sagging moments for BC is a parabola, because we have a UDL, and it is 16. So thank you, and don't forget to like, share, and subscribe.